imagine one input image with a motion vector of -1,1, as you can see here, we will get all those pixels. And if we have also two additional images, such this third one of motion vector 1,0, we will have those pixels. And finally, the fourth one is in here with a motion vector of 1, -1. We will have a complete high-resolution image based on 4 low-resolution images. Then the context will change, okay, and we will need to apply the algorithm one more time. Okay, so this is the idea of the super resolution. And it is very important to consider some parameters which can model the algorithm. These are the scale factor, the macro block size, the search area, and the window size. And of course, the low resolution images that we are taking as a reference in the process. The scale factor is the factor that we are using to multiply the resolution, to double or to multiply by 4 times or whatever. The algorithm that we are using has been tested from scale factors from 2 to 10. The macro block size is each macro block is one division of the image. The super resolution process is not applied to the image as a whole, but this is divided into macro blocks, and this parameter must be considered in order to get a good quality results. Around this macro block, we have a search area, and this is the area in which we will look for to find appropriate motion vectors from one frame to another. And finally, the window size is related to the number of frames that we are using in the super resolution process. So we have a continuum of frames in a temporal background, and we will need to select the number of frames that we are going to use in the process. This is the main steps of the algorithm. We have a motion estimation stage in order to get to see how one frame is moving to the next one. Then we will have motion compensation to compensate the motion vectors that we have calculated in the previous stage. And finally, if we didn't get appropriate super resolution information, we will fill holes with interpolation, and then we will get the high resolution image or video sequence. This is the test bench that we have used. We get an original sequence, and then we adapt this sequence to a decimated one, and then we interpolate, we super resolve, and we compare both results using objective quality matrix. These are the PCNR and the SSIM. PCNR is a traditional objective quality metric which relates the maximum power of a signal and the noise which corrupts that signal. And it's quite limited because it doesn't represent quite well the human vision system. So we have also used another objective quality metric, more novel, which is the structural similarity index. And in this case, this is very correlated to the human vision system because it is based on some parameters such as the loss of correlation, the luminance distortion, or the contrast distortion. So taking into account these, there are some research which compare some metrics with a factor sigma. This is from 2010 from Alain Aure. And so this can be related, but the SSIM is a metric more related to the human vision system. This is the idea on how we use the metrics. We take a low resolution signal, okay, taken from an original sequence. We select the parameters of the algorithm, and this is the interpolated sequence, and this is the super resolved one, okay? Then we will get some graphics to compare the PCNR and the SSIM, and in this case, for instance, we have an improvement of PCNR of around 1.5 decibels, and an improvement of the SSIM around 5%, okay? Okay, so these are the basics for the super resolution, and right now we are going to see some implementations, some real implementations that we have done in our institute. So let's begin with video compressor, okay, it's Picasso, and then we will be talking also about a digital signal processor, a field programmable gate array, a cell multiprocessor, and a network on chip. So beginning with the video compressor, this was based on a project in the Philips Research Laboratories in Eindhoven, the Netherlands. And this was done at the very beginning of the super resolution research line of our institute 15 years ago. This is based on a video compressor with a double view based on trying to design processing algorithms and include these algorithms in a video architecture that was previously designed, and at the same time in the architectural domain try to design encoding architectures to increase the functions of the whole architecture. So it's in a double view, and each part has feedback from the another one. This was the main video encoder. It has a spatial redundancy and temporal redundancy, and it already has 2 blocks related to motion compensation and motion estimation. So this was used as a basis of our algorithm. This is the architecture of the hybrid video platform. This is based on a control bus and a data bus, as usual, and is formed by several coprocessors, and it has capabilities to get a real time. It's based on low power, and it doesn't need to use external memories because it is based on a memory compression on the digital cosine transform domain. The first thing that we did was just to modify the architecture. We deleted the stream processor because it was not necessary for our application, and made some changes in some parts marked with asterisk in here. And then this is what we did with the Picasso project on the video compressor. And then what we check is to apply several tests with a different number of frames and to compare with the interpolation. This is a reference picture, and these are the low resolution input sequence, and we compare with interpolation, bilinear and nearest neighbor. Okay? The interpolation is fixed with independence on the frames that we are using in the process, but the super resolution has this behavior, so we get more quality when we use more frames. This has always some limitations, and it depends on the sequence that we are analyzing, but this is more or less the idea. And we can use some figures to show results. This is just an example. And sometimes it's quite difficult to see the improvement with the image itself, so we can use the image error to see to compare the super resolved image with the original one. And then we can also use another parameters such as the two-dimensional Fourier magnitude or phase. And we can see very clearly in here that there is an improvement with the details of the words and the background, and this can be much appreciated if we see the image error. This is the super resolve, and these are the two interpolations. Okay, in here it can be appreciated, the super resolved one and the two interpolations. And then finally, of course, we took into account what is the area and the power that we are dedicating for the device, and we compare with the state of the art of Hitachi and Fujitsu, and we got very good results in area, the minimum one, and power very close to the minimum one, which was the Fujitsu one. Okay, so this is the video compressor implementation. And now let's try to see how we applied super resolution to a digital signal processor. And in this scope, what I want to highlight is the process that we followed to try to get real time performance. So we had an initial algorithm, and we followed some optimizations in order to get real-time execution. This was done in 2008, 7 years ago, and this is based on a Texas Instruments device, which is based on fixed point operation. And the most interesting of this architecture is that it is based on a VLIW architecture. This is a very long instruction word architecture, so there is a parallelism in the instruction level, and we can follow up to 8 operations clock per cycle, which is quite appropriate, as we will see. This is the general diagram. Okay. This is the data path. Everything has a redundancy, 2 functional units, and something that was very useful was the caches that were included in the architecture. We can see the level 1 and level 2. And we use these caches for the faster operations that we needed to perform. And then we have also some video ports and the memory interface. And finally also some timers to control all the process. This is part of the general platform, is this device that we have in here. Okay. And it has also some other capabilities, such as read access memory, and the video recording ports and the video display ports. Okay. And just to connect to the whole board, we use this JTAG connector. Okay. This is the system setup. This is the JTAG connector that we have just commented to connect to the PC. We took the frames with a video camera, and we represented them with a beamer. This is the setup in our laboratory. Okay, but this is the part that I would like to highlight. This is what we did to follow real-time execution. We have an initial algorithm, which is called in here O1, and we went till an O8 optimization following some steps. First of all, we clean up the algorithm, removing everything that was inefficient in the O2 optimization. Then we saw the compiler options just to get the best options in order to remove control conditions and homogenize all the options. Okay. Then as I said, the DSP is based on fixed point operations, so we simplified everything, removing the floating point operations. We didn't lose important quality doing this, so it was a good decision, and we reduced computation time with this. We also use Texas Instrument optimized library functions in the next iteration, and then we used some other optimizations based on memory optimization, okay, based on this very long instruction word capability of the DSP. We also use the level 2 cache as an internal memory to make the algorithm faster, and we solve some issues related to the image size, applying overlaps in the image. Okay. So with this, we passed for each frame from 300 milliseconds to around 10 milliseconds. This is just an example, okay? So it was a very good optimization. So we were really close to real time in a common intermediate format, okay? As you can see in here. So we tried to improve even more the solution. And we detected that the most demanding task was related to the block matching, okay? And this is part of the motion estimation stage, which used a full search approach. So what we decided to do is just to get another motion estimation algorithm in order to reduce this task. We perform a study of different fast block matching algorithms. The ones involved are the ones that we studied finally, these 5 approaches. And what we wanted is, of course, not only an algorithm with a low number of operations, but with something with a high and stable PCNR. As you can see in here, the PCNR of full search and new 3 steps search are very similar, but the number of operations of the full search are a lot if we compare with the new 3 steps for different sequences. So we prepared a figure of merit which considered the robustness of the computation. This means the number of operations and the variance in the number of operations depending on the frames. And we got the best results in quality and its robustness computation for the new 3 steps algorithm. So we changed the full search to the new 3 steps, because as you can see here, for the new 3 steps, with these parameters of super resolution, we can get real time. And it is important to note that depending on the super resolution parameters, we will get one or another computation time. In this case, this is the search area, and these are the parameters for the macro block size super resolution window. Finally, to verify everything, we applied super resolution with a PC and with the DSP, and we compare, and it was the same, so it worked. We test the algorithm with several sequences. These are typical consumer electronics sequences, okay? Many of them with the common intermediate format, and even we also applied some cases with high definition television. These are the results. In here you can see clearly the improvement, okay? Some additional details. This is another sequence, the mobile sequence. We have a local motion in this part of the train, and also the calendar is moving in a vertical way, okay? And we get a good performance on the details of this part of the figure, as you can see here, and also in the numbers of the calendar. So what we did with the DSP is just to get real-time performance. And we got this for a common intermediate format size using the new 3 steps search motion estimation algorithm. This can be easily extended to other image processing algorithms, and if you want more information, you can read these papers from the Transaction on Consumer Electronics from 2008. Okay, so let's pass now to the FPGA. With the FPGA, we went into transaction level modeling. This, if you don't know this modeling, it is something that is based on a methodology to transform the system in a set of tasks with an abstraction level even higher than the register transfer level. It is usually utilized in applications for space exploration and early system validation. And the important thing is that we are not biasing the model with architectural choices. This is the methodology. It's in a top-down approach. We will have a general source, and we will extract the input files. Then we will get a model based on 2 modules, the sources and the main module. For instance, in here, the block matching. We will do everything for all the modules, as you can see here, splitting from the source. And we will get to the last module, okay, and we will rearrange everything in an ordered way. And finally, if everything works, we will encapsulate this as a general core. We have called this the SuperResolution core. Once we have done this, we will need to have a validation system. So what we did is to get the information from the original sequence, okay, from the original algorithm, sorry. And, okay, what we got is the motion vectors, the sum of absolute differences intra and inter. So this means in the same frame between different frames, okay. Then we will test both approach, the one of the natural, the original SuperResolution algorithm, and the one related to the core. And finally, we compare both of them, and if we get the same solution, then everything works. So one more time, we got that in general we have 70% of data transactions and 25% of control transactions. But one more time, the block matching is the most demanding code. So, the most demanding block. So what we need to do is again to work in the block matching algorithm to reduce the computation time. In fact, 70% of data transactions are based on this block, and 80% of control transfers also in this block. We check the algorithm that we perform in an FPGA with other approaches, such as the iterative back projection and the robust SuperResolution. And we got very good results comparing with these other approaches. This is a publication of Transactions of Consumer Electronics of 4 years ago. Okay, so we were encouraged, and we said, okay, let's go for something bigger. and we try to include this in the Celt Broadband engine architecture. This is basically the multiprocessor of the PlayStation 3. It is based on a main PowerPC processor element connected to 8 synergistic processor elements, working each one in more than 20 gigaflops. We have an external memory interface controller of 25 gigabits per second, and we began this research in 2011. As you can see in here, we have a general bus of more than 200 gigabits per second, and this connects the 8 synergistic elements, which are each one with 256 kilobytes, to memories of the main processor element, the level 1 and level 2 caches. And these are just some results to go faster. The most interesting in this case is that if we compare the serial version of the algorithm, the original one, with the parallel one, with big sizes, for instance, for CIF, we get speed ups of more than 250, which is a lot. Okay, this was just a comment for the multiprocessor. And for the network on chip, just some final comments. We also apply this in a network on chips based on a FPGA. In this case, we have 5 processing elements. One is for control, and the other 4 are for data. We have some other controllers, such as an DVA and a DDR3. Okay, as you can see here. And this began 2 years ago, and we are following a similar philosophy that the one that we followed in the cell processor. What I would like to show you is that the way in which we apply the 4 data elements is just to divide the image in 4 parts, as you can see here, and we get a decrease in the computation time. This is the integration of the algorithm in an FPGA, and this is more or less the idea on how to divide the processing. Okay, so let's pass now to some applications. The applications that I am going to introduce are real applications that we have followed, and we have too many different applications in SuperResolution. In fact, it can be even be applied to astronomic images. For instance, this is an example of the Mars Pathfinder image. This image was pre-processed, and the video sequence was composed of many frames. This is an example of the combination of 10 frames using SuperResolution. From this image is taken from the NASA website. Okay, this is just an example. These are other applications. The ones in bold are that what I'm going to explain and what we have performed in our institute. We began with very simple general applications such as still image enhancement, video improvement, and compressed info enhancement. And then we passed some more, let's say, real applications, which are now very important in the research lines, such as medicine, underwater environment, or multicamera imaging. So, beginning with compressed video, this is one project that we did in 2003, and in those times the trends in multimedia were based on low-cost mobile devices, such as you remember TV in cars, mobile phones, PDAs, etc. And as I began in my presentation, we were looking for low-cost, real-time, and low-power devices. And the scope that we followed was based in a digital audio broadcasting network. This involves that we are in motion conditions, so we need good quality in using rates of 1.8 megabits per second, and we wanted to use this in mobile receivers. Okay, so considering these limitations, let's show just the general idea of the project. The objective was the design of complex systems using architectures that can be configured. Okay, this was applied for the design of multimedia terminals for broadcasting. So this is the generation of the signal and the reception, okay? This was done by two universities, two Spanish universities, the University of Las Palmas, okay, and the Polytechnic University of Madrid. The Madrid was based on the IP extraction of the signal and the display, and we were more based on the decoder, the MPEG decoder. We introduced the SuperResolution in here to increase the temporal resolution, but it has some limitations. And what I would like to highlight in here is what we needed to do to introduce SuperResolution in the system. Imagine that we have this compression system, we have the encoder, then we will transmit, and we will decode, and we will apply SuperResolution. But if we proceed like this, the high frequency components would be lost because we have a low pass filter in the encoder, and the SuperResolution will be applied for anything because we won't have aliasing, we won't have high frequency components. So what we needed to do is just to get the required information for SuperResolution before transmitting, okay, before decoding. We have in here the decimation process to pass to a low resolution sequence. In here we can lose the high frequency component, so before doing this we need to get texture information and motion information, composing a TM map, which means texture motion map. Okay, I'm going to explain how we proceeded to achieve this, because we need to have three different regions. In which, in this one, we say that we have motion, and in the other two, we don't have motion, but we can have texture, or we can say that this region is flat. Okay? Let's try to explain this. With this information and the motion vectors, we can then apply the SuperResolution process. And the main novelty in this case is the TM maps. Okay? As I said before, we have three different regions. In the region 1, we have motion. If we have motion, what we are going to do is just to apply the SuperResolution process as it is usually applied. Okay? If we have a flat region, the SuperResolution is not going to improve anything, so we will just interpolate. And finally, we have the most complex case, which is the texture areas with no motion. In here, we need to apply SuperResolution, but we need to consider that the downsampling pattern is going to change from frame to frame. So we will see how to proceed. Okay? But before, let me explain how we say if a region is texture or non-texture. Okay? in order to do this, we just calculate the sum of absolute differences, okay, in the same frame for different blocks. And the most difficult is to calculate empirically a threshold, which will be what will say if we have texture or non-texture region, okay? And in a similar way, we work with the motion. But in this case, we use the mean difference between the different frames, okay? And again, we need to define a threshold to say if we have motion or no motion. In this case, we have these buoys that are moving in some way, and we have detecting motion in here, for instance. Then finally, we have defined 3 regions: the motion one, the one with no motion and flat. For instance, in this region we don't have any texture information, and in here we have textures. Okay, so we won't have motion, but we will have texture. Okay. This is another example, interview. Okay, this region is mainly flat. Okay, so no motion and flat. This girl is moving the hand and the head. Okay, we'll have motion in here, and the rest of the frame we have texture. Okay. This is the deadline sequence. Again, the jacket, no motion and flat. The books and the shelves, texture, and the head and the hand in here, motion. Okay, so finally what we do is just to divide the frame in some different blocks, as you can see in here, and say, okay, we have in here region 1, region 3, region 2, and then we can decide how to proceed in the next step. Okay? If we have motion, just apply the main super resolution process. Just put the pixels in the high resolution grid, okay, and get new positions in the high resolution grid based on the next or in the previous frames, and fill holes with interpolations if we don't have super resolution information. Okay? If we have region 2, we have a flat region, bilinear interpolation would be enough. Okay, this is the situation, this is a high resolution grid, this is the image, and we will just interpolate. Okay, and finally the most complex, the region 3. Okay, this is the example of the region 1, region 2. Okay, motion, flat and no motion, remember? But in the region 3 is more complex because we have texture, okay? So imagine that we are going to combine 4 frames. So the downsampling factor, the decimation factor is 2, okay? And the downsampling factor is changing, okay? This is the representation. Let's try to see this in here, okay? This is the downsampling pattern for each frame, okay? So if we are calculating the super resolution in this frame and we take the other 3, we will be able to get a perfect high resolution frame at the output if all the frames are based on region 3, okay? So perfect, let's say perfect, high resolution would be possible, but it is not always like that, okay? This is an example in which we are not getting the whole high resolution frame at the output because the frame k minus 2 is based on region 1, so it won't give information to the high resolution grid. This is the image k, it goes directly to the grid, and then for the k minus 1 we will get information, for the k minus 2 we have a different labeling. We are not getting information. And for the K+1, we are applying information. And the other pixels will be based on interpolation. Okay? This is just to show the importance of the threshold. Okay? This is the threshold related to texture, and this is the one related to motion. If we don't select this threshold in an appropriate way, we won't get maximum quality. Okay? With good thresholds, we get improvements of more than 5 decibels in the interview sequence. Okay? It is quite clear, the enhancement. This is the bilinear interpolation case, and this is the original sequence, and this is the super resolve. So there is a clear improvement from one to another. This is the deadline sequence. Again, it is important the threshold, but in this case it is not so key aspect, because if we don't use exactly the threshold, we will get also an important improvement. Okay, and here the improvement is very clear in the background from the super resolution case with relation to the interpolation. Okay, and finally the children sequence. Okay, improvement of more than 2 decibels, and in this case the improvement is clear in the background. Okay, just in here. Okay, so just some examples. And this is the distribution of the maps, and I would like to just to show some details. We are going to get some specific blocks from each one of the regions, okay? And remember, if we have region 1, we will apply super resolution, okay, and we will be very close to the regional sequence. And for the other regions, we will have interpolation, okay, the same solution, or if we have good frames for the region 3, we will get the same solution from super resolution to original high resolution. Okay. Okay, this is an example on what we have improved in the project. This is the direct decoding, and this is the decoding using super resolution. Okay. Okay, so let's go to digital zoom. We can imagine that the super resolution is in fact a zoom itself. So this means that we can save energy in the cameras using super resolution. We won't make the zoom with the camera, but with post-processing. Okay, this is the idea of this application, and for this, what we studied from the very beginning was to see if we have a local or global motion in the image. If we have global motion, this means that the motion vectors are quite similar for the different blocks. So the image is moving as a whole. Imagine an static background and one camera that is moving. And in the local, we don't have that situation. Every macro block have a different movement. Okay, so we will have one macro block, one motion vector, sorry, for every macro block. Okay. And what we did is the dynamic selection of macro blocks depending of the some absolute differences. This is based on a motion vector filtering capability. What we did is just to weight the motion vectors depending on the position of the block. Okay, this is the idea. We have a weight of 4 for the central block, and then different values. This is just an example for the 8 blocks that are surrounding the main central block. We got very good performance. It's the purple line, as you can see here, and we solve all the problems that we had with the model selections of the motion type. Okay. This is an example of the enhancement in the profiles of the words, as you can see here. And also in here in the circles, okay, yes, in here it's very clear the improvement also in the connector. Okay, so this is the idea of the zoom, of the domestic zoom. Okay, let's go to color. Color is normally based on Bayern patterns, and what we did is to analyze the acquisition system in order to see how we can apply super resolution, and this involved to find high frequency components, so aliasing. The color reconstruction is normally in here, just after the sensor, okay? And then we will have all the other processes, such as the matrix or color space, white balance, blah, 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 okay? And we will get the output of the super resolution system. Okay, we need to take into account that the lens directly act as a low-pass filter. So we are losing some high-frequency components from the beginning. This depends a lot on the fill factor, which is around 25% in lenses, and if we go to micro lenses, it is around 62%. Okay. In the Bayesian pattern, we have an important aliasing source in every color plane. So just after the sensor, we need to think on how to apply super resolution. We were based on two color reconstruction algorithms, one standard, directly based on bilinear interpolation, and one was property of Phillips, smart green 3. Okay, this is the idea. We have the standard color reconstruction and then the bilinear interpolation, and then we apply super resolution. If you see, the results are quite similar, and this is because we are losing the high frequency components, we are removing the aliasing, and we are not improving anything. Okay, so this is the same process with the smart green 3. The difference is that in this case we are managing the green value information. We are trying to get the green values with the blue and red ones, multiplying by some empirical components, and this will increase the green resolution as a whole, and in turn it will increase the luminance resolution and the image resolution. Okay, this is the smart green 3 plus bilinear interpolation and super resolution. Okay, we have a better solution than the one before, but again we are not making the most of the super resolution because it is limited by the bandpass filtering. Okay, we are removing the aliasing, so we need to try to find an alternative. In this case, we are reconstructing some edges. Okay, but we need to find an alternative. And an alternative could be to change the color reconstruction algorithm and use directly super resolution. This could be a solution. Okay, and the motion vectors will be based on the green color one more time. Okay, so we will apply super resolution to all the color planes. Okay, and as we have more information in the green component, this will be used for the motion vectors. Okay, this is the standard color reconstruction, the smart green, and the super resolution. Okay, and here we can see a small improvement in the background. Okay, but it's not quite important, that improvement. And if we need motion to get the super resolution solution, and if we don't have motion, the poor motion estimation will make that the super resolution will go again to the standard reconstruction algorithm. So it is not a quite suitable solution. A suitable one could be to combine both the color reconstruction and the super resolution. This is very interesting, but because we will have two aliasing sources. One is related to the magnifying of the super resolution, and the another is related to the color sampling. Again, the motion estimation will be used with the green color, and this is more or less the case. We are going to amplify, to magnify the grid, and we will apply also to super resolution. In this case, this is the bilinear interpolation zoom, okay, with a SmartGround 3 and the standard case. And this is a super resolution case. In here, it is an improvement. Let's go to the detail. You can see in here in the edge, okay, in comparison with the super resolution, and also in the background of the figures, okay. So this seems to be a good solution. Also, in here, in the details of the words, and also in the color is being improved, and especially you can see in here the chain. Okay, in here is quite straight. Okay, we are improving in this case. So this is more what we did with color reconstruction. And finally, we are entering in the most novel solution that we are applying. First of all, I will talk about multi-camera imaging. Till now, we have talked about temporal information. We are getting more information using forward and backward frames, okay? But we can also use spatial information considering different cameras. If we get, for instance, in here 3 cameras and we got the overlap image, we can even get more information. Let's see an example. Imagine that we have 4 cameras, okay? 1, 2, 3, and 4. We'll have an overlap in all the cameras, and then we will have other regions, and we are going to see in detail how much information are we getting. Okay? And this is based on something that we called pre-processing modes, which are full frame when we are using all the information that the 4 cameras are taking. Overlap, we are only using the overlap information, and overlap plus borders, we are using the overlap and also the borders, and we are combining this information in some way. And for this, we need to know how much information we have for the different cameras, okay? In the overlap region, which is this one, we are getting information, of course, from the 4 cameras, okay? The 4 cameras are providing information in this case. For regions 2, 4, 6, and 8, we are getting information only from 2 cameras, and in the corners, in the 1, 3, 5, and 7, only from 1 camera, okay? So depending on the region in which we are moving, we will get more or less information, okay? And once we have selected the preprocessing mode, okay, this is a general diagram of the algorithm. The first thing that we do is to reorder the frames which have been taken from the cameras. Then we apply a preprocessing mode, and finally we consider one of these methods, okay, which are called temporal spatial superresolution, spatial temporal superresolution, and mixed superresolution. And this is just based on how we use the information. I mean, how we apply, if we apply first temporal superresolution or spatial superresolution, okay? In the case of the temporal superresolution method, what we do is just to go to a medium resolution sequence, applying temporal superresolution for every camera, and then with all the sequences that we have at the exit, apply again spatial resolution and get a high resolution sequence. Okay? Then in the spatial temporal superresolution, what we do is just to apply to one of the cameras a spatial superresolution and then the temporal one. Okay? And the mixed method is a combination. In the mixed method, what we have is these windows that we call mixed working window for the frames taken from the 4 cameras in different instants of time. We are considering different working windows, and then we apply super resolution, and we get finally the high resolution sequence. We have got very good results with this approach because we have a lot of information which is really good for super resolution, and this information is quite correlated. We have mainly got good results for mixed super resolution methods, and for in some cases also the temporal spatial super resolution is a good choice. But we have mainly decided to use the mixed super resolution because it's the one in average which provides the best results and also reduce a lot the computation time. In here we can see some examples for real multi-camera images. These are very complex sequences, okay, but even we have get improvements, as you can see here. And for other general images, as for instance Stockholm, we have got a very good results, as you can see in here, for instance, or in here. And this is a publication of last year in August 2014 in the transactions on consumer electronics. You can take a look. Okay. Then we are going to explain very fast just some examples related to the underwater environment and medicine, okay, which are so typical applications for super resolution. For the underwater environment, what we have done is just to include georeferencing in the application, okay? And for this, we have considered that for different frames, okay, we have a different georeferencing information, okay? Let me explain this. This is just a general map. The green lines represent motions of underwater vehicle, okay? And we have the spatial and temporal information for every frame combined with the georeferencing information. So for each frame, we will have some frames with georeferencing information, which are called keyframes. And with this information and the number of frames that we have from one frame to another, we can get the average speed of the vehicle. And what we did is just to decide the number of frames to be used in the super resolution process depending on the speed vehicle. So if we have a faster speed, then we will use less frames in the process. It worked very well, and these are some results. This is the results for the georeferenced super resolution, okay, which is improving the interpolation and the baseline super resolution that we had before using this element. And the improvements are mainly based on the reduction of artifacts in the super resolution process. This is a baseline case, and this is the georeferenced case. Okay, for medicine, what we did is considering some tissue samples from a microscope, just to combine all of them. We have several low-resolution images. We have some motion between the images, and then we just apply super resolution, and we got very good results because we passed some pre-processing before applying super resolution, okay? Based on typical image improvement pre-processings, based on histogram, equalization, gamma correction, etc. And we also put in the middle a discriminator to avoid using low correlated frames. These are some examples. We can see that the super resolved sequence frames versus the interpolated in the background has less noise, as you can see here, which improves the visualization too much. Also in this frame, we have more details, you can see here, and this is another example, okay? Okay, so once we have concluded with the applications, let's see some of the current work that we are performing at the moment. We thought now, okay, we have all the parameters, and it is quite difficult sometimes to decide what are the best super resolution parameters to be used in the process. And this is not, of course, for a real-time application, but we can see, okay, we are going to decide the best parameters that can be used in the process. So what we did is just to use a supercomputer. A supercomputer that we have in the university. It's called Atlante. And we analyze a massive quantity of sequences with different parameters. And we check the values of PCNR and SSIM based on the parameters. With this approach, we can get the best solution. This is, of course, not practical for real time, but this gives us information to make decisions on how to improve the algorithm. This is the solution, for instance, and you can see here that the result is almost an original image. It's very, very high quality result. Some details, as usual. You can see here that even the smallest words can be read. And with this information, we decided to perform, this is something that is under progress, a selective filter. And this is based on the fact that we have the current frame and some previous and forward frames. We're going to use the SSIM, which is a very good objective metric, to decide the frames that we are going to use in the super resolution process. Okay? If this comparison is exceeding a threshold, we will say yes, or on the contrary, we will say no. We will apply the process to the rest of the frames, and we will select the most appropriate frames to be used in the super resolution process. Okay, this is an example of the Foreman sequence. We have global motion as a whole and some local motion in the eyes and in the head of the man. Okay, we are considering 30 frames. This means 1 second. And as you can see in here, when we move from interpolation to super resolution, we improve some parts of the head of the man. But as we have the local motion, if we consider all the frames, then we will get these annoying artifacts. And using the filter, we are avoiding that situation. Oh, sorry. I don't know what happened. Okay. This is quite good because this is the solution, okay, the green one for PCNR and for SSIM. And we are not only improving the quality, this is the baseline super resolution case, but as we are using less frames, we are also reducing the computation time. But of course, the most difficult, as usual, should be to define the appropriate thresholds that are being considered in the super resolution process. Okay, then we thought that this works, but it is quite important also that if we are always using a fixed block size in the algorithm, then in some cases we won't get improvements. This is something that has been applied in the past, but we are combining this with the filters, and this works very, very well. As I said before, the most important is to define the thresholds that we are using in the process. In this case, we are using a combination of SSIM and the mean absolute difference. With this combination, we decide if a block must be divided or not, and this combination have shown very good results. We can see here that even in the improved sequence that I saw before, okay, there were some macro blocks in which we didn't get improvement because we have the annoying artifacts one more time, and this is reduced using the variable macro block size super resolution. Okay? And finally, what we are doing at the moment is to combine the multi-camera imaging application with the filters. So just to take the mixed super resolution algorithm that I showed before, and to include the coarse filter based on the window selective filter and a fine filter at a block level, getting a very high quality super resolution sequence. This is an example. This is the proposed algorithm, okay, and this is interpolation. It is quite clear what has been the enhancement. This is an intermediate solution. This is a baseline super resolution algorithm, and this is the one filtered, okay? The improvement is quite noticeable in this case. And we have also tested this with some underwater sequences, and we have got very good results. You can see here the profile of this fish, for instance. The improvement is very important. Okay, so I will talk more about this theme of multi-camera imaging applied to super resolution on Monday at 20 to 3 in the session Image Video Processing, if you are interested in attending. Okay, and with this I'm closing the tutorial. I'm leaving this slide just to summarize all that I have told today. We have talked about algorithms, about the general concept of the super resolution, the filtering, how to use the weights, this adaptive macro block approach. We have also mentioned how to speed up these algorithms, how super resolution can be combined with compression. We have introduced some implementations and applications related to super resolution, and we have introduced some projects in which we have worked with super resolution. So I leave this in here just for the questions as a summary, and thank you very much for your attention, and I am here for any question you want to do.